So next, let's talk about the Newton's method. So Newton's method is somewhat similar to your gradient descent. So again, it's going to have a lot of iterations, and in each iteration, it tries to move to a better point. But there's one thing different. The gradient descent method is a first order method. Okay? Pretty much we always calculate the gradient and then try to move to somewhere. So the first order method is intuitive, but sometimes it may be too slow. Okay, so we're not going to show you why it may be too slow, but at least one thing that is clear is that we have gradient, we have Hessian, we have first order, we have second order, but we have not used any second order thing when we are using the gradient descent method. So maybe we may try a second order method which relies on the Hessian to update a solution. That may be faster, right? So maybe we should try this. And one second order method that is very popular or very fundamental, I would say, is the Newton's method. So to introduce the Newton's method for nonlinear programming, we need to start by introducing the Newton's method for solving a nonlinear equation. Maybe some of you also heard about this when you were taking your calculus course. But anyway, let's try to do this. Suppose I have a function which has only one decision variable or one independent variable. Okay, let's say this function is differentiable. We want to find x bar such that f of x bar is 0. Okay, so f is a nonlinear function like this. Okay, f is a nonlinear function, and we want to find a root for this nonlinear function. So we are trying to solve a nonlinear equation. So now our strategy is the following. Still, I'm going to start from an initial point. And then at each point xk, I'm going to consider the linear approximation of f at that particular point. So pretty much we are doing this. For this function f, I'm going to create fl of x, where L means the linear relaxation. And how to do that? Well, this is pretty much the Taylor expansion you learned in your calculus course. So at each point here, you first do f of xk plus f prime of xk multiplied by x minus xk. Okay? So at each point, you first ask yourself, how high is your current point? So that's your f of xk. And then you have derivative. Okay? So your derivative here somehow means your slope. And then you have x minus xk. So you were going to move to somewhere that is close to you. Okay? And you know how is the impact of doing the moving. That's going to move you to that direction by decreasing or increasing some amount. Okay? And that amount is determined by the slope and the amount you move. Okay? So if you express the height of x in that way, then your FL, of course, is a linear function, and it's pretty much a first order Taylor expansion at the point x0. Okay, so as we mentioned here, this is the tangent line, this one, of f at xk, or the first order Taylor expansion of f at xk. So your f originally is nonlinear, but its first order Taylor expansion must be linear. Then what we will do is that we will solve this linear equation. We will try to make xk plus 1 satisfying the function being 0. So we don't really directly solve our nonlinear problem. For this nonlinear equation, maybe we don't know how to solve it. But for the linear one, everything is so easy. Okay? So we do that once. And then we do it twice, do it 3 times, 4 times, and so on. We keep iterating this until our f of xk is less than epsilon. What's that? Our f of k is pretty much the objective value, okay? and we want to make f of xk 0 pretty much. So we would stop when this value is pretty much 0, okay? Or on the other hand, maybe some people would say, okay, if the difference between the x value is small enough, then we would also stop. So we have some stopping conditions, and pretty much the way that we stop is to think about what's the current improvement. If the current improvement is already too small, then we stop. Or when we see the objective value is already close enough to what we want, then also there would be no much improvement, then maybe we also stop. So pretty much that's the way for using the Newton's method. Okay, so the method is invented by Newton. So using the Newton's method, we are able to solve a nonlinear equation.